All right, now officially happy Friday to each and every one of you. And we'll just have another lecture for today. Let's start off with some housekeeping announcements. First of all, I want to mention that we will have a lab today. So if you want to do the lab, please come. We would like for you to come. So lab right after class. All right, the second thing I want to mention to you, Robert, one of your classmates brought this to my attention. I'm meeting a student tomorrow at 11. Their email went out to everybody, the whole class. So, hey, everyone can come. So I will have office hours tomorrow. You do not have to come, but if you do, that's not a problem. So I will have office hours Zoom from my house tomorrow at 11 a.m. So if you want to attend and have any questions, comments, just have a conversation. Does not have to be about chemistry. I'll be in from 11 to 12, and I think you all inadvertently got the Zoom link. But I know one person, he's quarantined, and I'm going to meet with him, but you guys can also come and join us at that link for any questions or comments. Turn in, point number 3, turn in your chapter 11 homework. All right, I'll put the 10 points in. I think it's a little bit past due now. And then turn in your chapter 12 homework, I think by next week. Late next week. Just take a picture, scan it. Which one? Chapter 12. That's fine. You can turn it in. I just put in the 10 points. So I made those due dates in advance, and I did not know, where we were in the course. But if you can turn it in next week, or the minute you get it done, you can turn it in, and I'll put in the 10 points. Okay. But don't turn it in like in May. Okay, turn this in within this weekend or next week. All right, work on quiz 1, and we have an exam coming up February 15th. So I'll give you more information about that. Your first exam is February 15th. All right, so use the study guide on Blackboard, and I'll have office hours the night before the exam. But everything that's on the exam is on the study guide, and I'll also go over the exam maybe next Friday. Okay.
Are we doing that on Canvas or?
Yeah, it's all on Canvas. Okay. So yeah, it's all on Canvas. All right, so quiz 1, my system is that the quizzes are due the day of the exam. So your quiz 1 is due also the 15th of February, and I believe that's a Monday. All right, and finally, we're doing the lab today, Friday. So your lab report for that will be due 1 week later, next Friday. Either with me, you're doing it after this class, or you do it watching the video. Because a couple of our classmates are quarantined. I just got the email. So obviously they can't come to the lab. So they'll watch the video. If you want to watch the video, do the lab report. Fine. If you want to do the lab, I know last semester we had 2 students back there that came to every lab, perfect attendance. So let's see if they do that again. If not, that's all right. I know they'll watch the video and turn in a lab report. So lab report next Friday due. That's the 12th, correct. And the lab is intermolecular forces. Okay. The lab we will do next Friday is freezing point depression. Okay, so new lab next Friday. All right, any questions or comments? Anything you want to discuss in terms of due dates, and where we are at in the course. Also want to tell you that Test 1, your first exam, will cover chapters 11 and 12. 11 and 12. All right, the study guide on Blackboard, I believe, study guide on Canvas, I believe should tell you what's on the exam. All right, without further ado, where we left off on Wednesday's class was talking about the conversion of molarity to molality, molality to molarity. This is very tricky, okay? It's kind of not so simple, and I personally also myself kind of struggle with these types of problems. This is where we left off. So first of all, let's go over this. The molal, which is small m. What is molal? The definition of molal, a good multiple choice question. What is the definition? It is moles of solute over kilogram of solvent. Okay, that is a concentration. And we want to convert that to molarity. And what is the definition of molarity? Big M. Okay, once again, that's a good multiple choice question on the exam. Molarity is moles of solute over liter of solution. Okay. So the goal here is to convert between one and the other. Right, so multiple choice definitions of these units. So 8.010 molal is the same thing as 8.010 moles of H2SO4 over kilogram of solvent, which is the kilogram of water. We'll say the solvent is water. Right? Good assumption to make. Right? Well, 1 kilogram of water is the same thing as 1,000 grams of water. Is it not so? Okay, that's what it is. So now, grams of solvent plus grams of solute equals grams of solution. Solute plus solvent equals solution. So we got 1,000 grams of our solvent. All right, where will we get the grams of solute? I'll box this in green. The grams of solute comes from here. Okay, converting the moles of H2SO4 to grams of H2SO4. Oh, did you see this? This is green, and it's coming yellow. What?
Yeah, I thought it was my eyes,
But it's coming green here.
We live in a simulation.
Yes, you're right. See, this is green. It's green here, but on the projection. Oh, it's physics. You had physics class last hour, right? No, none of you had physics class. Dr. Singh will explain that. That's strange voodoo. It's green here. See, look. Can you see the green? You see the green, Josh? But it's yellow. Or it could be a sign, but I don't know if it's good or bad. So we convert this moles of solute to grams of solute. You guys in the back, you can't realize what's happening here. You have no idea what we're talking about. You must think all us in the front row are a bunch of dummies. Or what are these weirdos talking about?
well, like it's yellow. What do you mean?
Oh, look at this. It's green.
Yeah, it's that color on the paper. I can see it.
See? So converting this to grams is the grams of solute. Okay, so there's our grams of solute. Grams of solute plus grams of solvent equals grams of solution. All right, we add them up. We're getting 1785.2 grams of solution. All right. All right, so now from grams of solution, we'll go to liters of solution. Okay. So we'll use our density, 1785.2 grams of solution. So one thing I want to mention, when you do these problems, you have to be given a density, all right? You have to be given a density, otherwise you can't solve this problem. Times the density here, I don't know if you guys in the back can see that, is 1.354 grams per mil. Let's go ahead and convert that mils to liters. So 1,000 milliliters is 1 liter. Right, the grams of solution cancel, the mils cancel. So 1785.2 divided by, let me put parentheses here, divided by 1.354 times 1,000. 1.318 liters of solution. Okay, so stop me if you are having any issues. 1.318. I'll just put an extra digit, liters. All right, and I think we can solve this problem now and get our final answer. Big M is moles of solid, liters of solution. I'm going to hammer this, many times. Moles of solid, liters of solution is big M. And that's going to equal to 8.010 moles. We got our liters here. 1.3184 liters. Okay. 8.010 divided by 1.3184. 6.0, let's see, they put it here in 4 digits. I'll do 4 digits. 6.076. Big M, 6.076. Yeah. Okay, don't forget the units. And that's going to be our correct answer, 6.076. All right, so the bottle is 8.010. Excuse me. The bottle is 8.010 molal, same thing as 6.076 molar. So we did about 3 examples of this Monday, and today. Just be aware of these types of problems. There are a lot of pitfalls that could happen. It's a little bit confusing. So check some videos. Clutch prep for those that have. I also want to tell you I got an email. Okay, she wants all of you to join Clutch Prep. So please do that, and I think that should also help you. Okay. While we wait for everyone to write everything down, I want to tell you, for those that are following in my notes, you can skip page 6. So I'm not going to do anything with page 6. I move on. Okay, so page 6, I'm not going to cover it just for time factors, but I will cover page 7 now in our notes. All right, so definitely we will see this on the exam, and that is colligative properties. All right, so we talked a little bit about this, I think, last week, or maybe Monday. There's 4 colligative properties. You see, I could have water, 1 beaker, but here I'll have water and glucose. Okay, glucose or sugar, C6H12O6. The minute I add a little bit of glucose, or vitamin C powder, or Kool-Aid powder, or whatever chemical, you name it. Okay, how simple, how large, how complicated, how heavy, how small. The minute I add that, and provided and provided it's soluble, we have a solution. And 4 fundamental things happen to this solution that's very different than solvent alone. Okay, in this case, I'm taking the example of the solvent to be water. So 4 fundamental things happen. And those 4 fundamental things are the vapor pressure lowers. Okay, so we call that vapor pressure lowering. Right, we have a new boiling point. This boiling point is going to be higher. We have a new freezing point that's going to be lower. Okay, that's next week's lab, freezing point depression. And we have, okay, don't forget the vapor pressure is going to lower. And then we also have what's called an osmotic pressure, and this is for people that are in biology. An osmotic pressure in the presence of a membrane. Okay, in the presence of a membrane. In presence of a membrane. So those 4 things are happening. We call them collectively colligative properties. Okay. Let me make a comment on vapor pressure lowering. Okay. So let's go back to this little example here. So you guys, you see here I just have plain old water. Okay, which is nice. But here I have not only plain old water, but I also added a little bit or a lot or however much to get into solution. I added some of this solute. So remember our definition of vapor pressure. Okay. Evaporation, condensation, evaporation, condensation. So for this to evaporate, become a vapor, come back down, exert a vapor pressure, okay, you have to overcome solvent. Okay, for if it's water, you have to overcome hydrogen bond. You have to overcome solute. Okay, so the glucose molecule will have some interaction with another glucose molecule, hydrogen bonding, polar, all that stuff. And then we have to overcome solute solvent. So we got to overcome all these intermolecular forces. Overcome all these intermolecular forces. Here, all we have to overcome is just the solvent, which is hydrogen bonding. Here, we just have to overcome H2O to evaporate, and H2O is, we'll just have to overcome hydrogen bonding. Here, we got to overcome all these 3 different facets. And that is why the vapor pressure is lower when you make a solution. So this is why vapor pressure is lowered when you make a solution. So let's talk about the formula here. The formula is shown right here for you guys. Okay, we got a new vapor pressure of the solution. It's going to equal to, that X is called mole fraction, and that P naught solvent is the vapor pressure of the solvent alone. Okay, vapor pressure of the solvent alone. So let's designate let's talk about this here. So first of all, this X solvent is called the mole fraction of the solvent. Okay, mole fraction of the solvent. Okay, part over whole is a fraction. Okay, part over whole is the mole fraction. So here, the mole fraction of the solvent, okay, is going to equal to the mole of solvent divided by solute moles plus solvent moles. So that is what that mole fraction is. And then this P naught, that is a symbol called naught, that little O there. Naught. And it's P naught of the solvent. So this is the vapor pressure of the solvent by itself. Okay, that's what we'll look up. Of solvent by itself. Okay, remember, vapor pressure is quoted at what? A specific what? Specific temperature. Vapor pressure is quoted at a specific temperature. So whatever temperature this problem is at, you're going to have to go find the vapor pressure of that liquid at that temperature. So vapor pressure is at a specific temperature. I'm going to say quoted at a specific temperature. Pure solvent, nothing is added to it. Vapor pressure of the pure solvent. All right, so let's do a problem that talks about this here. All right, practice problem. All right, calculate the vapor pressure of a solution, solute plus solvent. We want to hammer that home. Made by dissolving 82.4 grams of urea, and they give us the molecular weight, and 212 milliliters of water at 35 degrees. Remember, vapor pressure is quoted at a specific what? Temperature. So what is the new vapor pressure, or what is the vapor pressure lowering? Right, so let's first identify our solute and solvent. Okay, by default, our solvent is anytime you see water, okay, automatically go for that as your solvent. So I'll call it water, okay, distilled water. And our solute is going to be urea. All right, one thing you need to know to solve this problem that's not given to you is the density of water. So on any exam, I will give you the density of water or any other information. But to solve this problem, you'll need the density of water, and it's actually just 1 gram per mil. Okay. All right, so we identified our solvent, we got our solute. The density of water is 1 gram per mil. I'll give you that on an exam. And let's go ahead and calculate the new vapor pressure. So what's going on here? We have water. What is going on here? We have water. And they tell us we have 212 mils of it. Tells us it's at 35 degrees C or so. And now we have water plus 82.4 grams of this substance called urea. Right, so what is the new vapor pressure? What's the vapor pressure of water at 35 degrees C? All right, for that we'll use this table here. And I know you got to squint because remember, vapor pressure is quoted at a specific what? Temperature. So vapor pressure here is 42.18 and the units are millimeters of mercury. Okay. So that's water by itself. Remember, I got this from the table. Okay, what's the vapor pressure after we add this many grams of urea? Right. So here's the equation. I'll give you this equation on the exam, so no need to memorize it. P, the solution, solute plus solvent, is the mole fraction of the solvent times the vapor pressure of the solvent alone, totally by itself. We call that P naught. So I'll give you this equation for vapor pressure lowering. Right, mole fraction of the solvent. Okay, this is something we need to solve. So we have 212 mils of water. Okay, the density of water, this is why I had to give you the density. The density of water is 1 gram per mil. And we know that for every, the mils of water cancel. And we know that for every 1 mole of water, okay, looking this up in the periodic table, the number for hydrogen and oxygen, add them up, and it's about 18.01 grams of water. So the grams of water cancel. So 212 divided by 18.01 grams, I'm getting about 11.77 moles of solvent H2O. Solvent. All right, let's figure out the moles of urea. Okay, we got our moles of water here. The moles of urea, 82.4 grams of urea. Times for every 1 mole of urea. The molecular weight is 60.06 grams. Grams of urea cancel. And 82.4 divided by 60.06 is about in my calculator, 1.37 moles of urea. Okay, and again, urea is our solute. I think we have everything to solve and plug it into this equation here. Okay, mole fraction of the solvent. Mole fraction of the solvent It's going to be the moles of our solvent up in the numerator, 11.77 moles, divided by part over whole. That's what a fraction is, part over whole. So we're going to add these 2 moles. 11.77 moles of water plus 1.37 moles of urea. Okay. Part over whole. All of that times the the vapor pressure solvent alone, and that is this number here, 42.18 millimeters of mercury. So let's do this on our calculator here. Okay, this thing in the brackets, this thing in the pink brackets is the mole fraction. So it's going to be 11.77 moles of solvent divided by total moles. 11.77 plus 1.37, close those parentheses. So 88.895 or 89.5% moles of water. Okay, so 0.8957 blah blah times the vapor pressure of solvent alone at 35 degrees C. 18. I'm getting an answer about 37.78. 37.78. Okay. And don't forget the units, millimeters of mercury. And that's going to be our final answer. Notice the vapor pressure has lowered, which is vapor pressure lowering. Okay, the minute I add so much urea to so much and so much water, my new solution will have a vapor pressure that's much lower than before. Notice it's lowered, right, from 42.18 to 37.78. Okay, let's do this problem here. All right, another problem with regards to vapor pressure lowering, but this is a little different. Okay, here we're dealing with organic substances. Okay, organic. So another name for organic are volatiles. So how many of you plan to take organic chemistry after this class? Okay, several of you. Okay, so in organic chemistry is the chemistry of volatiles, the chemistry of carbon, but carbon also is in many of these functional groups. Alkanes, remember dispersion forces, alcohols, ethers. Okay, so all of these are what we call volatile. All right, so we do something a little bit different. So these are what are called organic. Stuff up above here, it's more inorganic. Okay. So what we have to do here, we just add the vapor pressures together. Okay, so here we just add the individual vapor pressures. To get the vapor pressure of the entire solution. Okay. This is the situation for volatiles or organics, which you will talk about more in detail in organic chemistry. Okay. Okay, what do I mean? Let's do this one problem. All right, so what is the vapor pressure of a methanol? That's just the abbreviation for methanol. And ethanol solution. Okay, so methanol and ethanol. where the mole fraction of methanol is 0.576 at 25 degrees, mole fraction, and at 25 degrees the vapor pressure of methanol is 127 millimeters of mercury. Okay. Vapor pressure quoted at a specific temperature. Okay, at 25 degrees the vapor pressure of ethanol is 58.6 millimeters of mercury, vapor pressure of ethanol at this specific temperature. All right, so let's reread this and see what we're trying to solve for here. Okay, we got the vapor pressure of a methanol-ethanol solution. So I got some methanol here. Okay, I got some ethanol here. Okay, the good stuff. All right, will these two mix at the methanol and ethanol? Yes or no? Miscible or immiscible? Miscible or correct? Miscible. Okay, like dissolves like. Okay. All right, so we got all of these two mixing together. Okay, we got the mixture here. So notice we don't have a solute. Okay, we just mix some, this is isopropanol, but we mix some methanol and ethanol. They mix together. And they tell us that methanol by itself has a vapor pressure of 127 millimeters of mercury. Again, we always quote this at a specific temperature. And they also tell us that we have ethanol by itself. This is by itself now, is 58.6 millimeters of mercury at 25 degrees. Okay, so I drew this based on the problem. All right, what does the problem also tell us? I'll highlight this in pink. The mole fraction of methanol is 0.576. Okay, if the mole fraction of methanol is 0.576, what's the mole fraction of ethanol then? Should be able to solve it. What's the mole fraction of ethanol? What do these have to add up to? To add up to mole fraction of this plus mole fraction of that should equal to 1. Okay, part plus part plus part plus part, okay, should equal 1. Okay, so all of this should equal to 1. Okay, the mole fraction should equal to 1. Okay, part over a whole is a fraction. So what is whole? What is whole? Whole is 1. Okay, the pie is 1. Okay, the pizza is 1. Okay, we take a bit out of it. 0.576 out of that is methanol. Then what's the leftover? Ethanol, which is 1 minus 0.576 is what is that? 0.424. 1 minus 0.576. 0.424. Okay, mole fraction. That X stands for a mole fraction. All right, now all we got to do is just add this up. So we need the vapor pressure of this guy, okay? The total solution. Well, we got the vapor pressure of this alone. We got the vapor pressure of that alone. We got the mole fraction of this guy. We got the mole fraction of that guy, because remember, methanol, ethanol, they combine to equal 1. All right, so let's put it into our formula here. All right, the pressure, the vapor pressure of this total solution, which again is methanol and ethanol, okay, is going to equal to the vapor pressure of ethanol plus the vapor pressure of methanol. This is what I mean when you say you can add them up if they're organic. All right, what's the vapor pressure of ethanol here? It's going to be 58.6 millimeters of mercury times the mole fraction. And what is the mole fraction? 0.424. Okay, plus the vapor pressure of methanol by itself, which is 127 millimeters of mercury, times its mole fraction. And they tell us in the problem it's 0.576. Okay, remember, I'm just following the equation here. Just following this equation. Mole fraction, vapor pressure by itself. Mole fraction, vapor pressure by itself. Ethanol, methanol. All right, so 58.6 times 0.424 is 24.85. I'll just round it up. Oops, sorry. Okay, the units here are millimeters of mercury, plus 127 times 0.576. Uh, 73.15 millimeters of mercury. So adding these two up, 5 plus 24.85, about 98. Okay, and that's our answer. So kind of in the middle, right? Ethanol is 58.6, methanol is 127. You mix them up, and the vapor pressure of the mixture is kind of right in the middle between those two numbers. Okay? All right, the last 5 minutes or so of class, we will go over the second and third colligative property. So this is vapor pressure lowering. So let's just go over the next couple of colligative properties. One of them is boiling point elevation. Okay. This thing here is called a phase diagram. Okay, remember phase diagram? Okay. All right, phase diagram. So what we see here in pink is the phase diagram of the solvent. Okay, when we add the solute to the solvent to get a solution, the phase diagram shifts. Okay, this is going to shift this way. Okay, to the here. And this line here, the solid liquid demarcation, is going to shift that way. Okay, so we see two shifts here. Okay, the net result is we're going to have a new boiling point that's higher. And then because of this leftward shift at the solid liquid line, we have a freezing point that is lower. Okay, because of this shift in the liquid vapor line, we will have a boiling point that is higher. So they shift. Okay, the shift is shown here in yellow. Okay, so we actually get a new phase diagram. So here I'll put in yellow solution. Okay. Solution. All right, so let's talk about these equations here. I'll give you these equations on the exam, so you'll need to know how to work them. The first one here is the change in the boiling point, the new boiling point. We add a solute to a solvent. We get a solution. New boiling point, will that be higher or lower? Okay. New boiling point will be higher. Okay. So we want to determine the value of the new boiling point, and that's right here. Okay, so Kb, K of B is a constant, so that's the molal boiling point elevation constant. Notice the word here, molal. Okay, molal, not molar, molal. And then we take that constant, so it will be given. Okay, or look it up in a table. You take that times the molality of the solution. And how did we say the molality is? This is an error. Okay, so sorry about that. And what did we say molality was? It's moles of solute over kilogram of solvent. Okay, I wrote moles of solute, kilogram of solute. That's an error, obviously. So we will cross that out. So that is molality. Okay, and this will tell you the new boiling point. Okay, and the new boiling point is going to be, as Elena mentioned, higher. Okay, finally, we have the exact same formula for the freezing point. The freezing point is going to be what? Higher or lower? Okay, it's going to be lower. And by extension, it's going to be delta TF. The F stands for freezing. K of F times molal. Okay. So K of F is the molal freezing point depression constant. Molal freezing point depression constant. And M is molality. Just pretty much the same thing as the boiling point equation. Units here of Kf, this constant that you will look up or will be given on the exam, the units of this K, F or Kb, the units are going to be degrees C divided by molality small m. Okay, degree C divided by molality small m. Units of the constant. All right, and so on the next page here, we see pretty much the same thing. I'm going to move to the next page. And the next page is pretty much the same thing. Again, pardon this error here. Molality is moles of solute over kilograms of solvent. here's this equation here, delta T of F. All right, so next week we'll do some of these problems. Some of these problems you'll see on your problem set of the exam, and you see it in the multiple choice. And for those of you that want to do the lab in person, should be made available. And have a good weekend, everyone. All right, this lecture should be up by tonight, and I'll also scan these notes.
We still only have the one lab like every 2 weeks, so we can split.
Right, we're
So
going to
like
have a
this-
lab every 2 weeks.
So this is the second week though for the first
Right,
lab.
this is the second week for the first lab, okay? So if you did the lab last Friday, I know we were online. It's fine, just make sure you upload the lab report, okay? And we're going to split it 8 and 8. So, yeah, starting next week. Hopefully we won't have to be sent home, okay? And Larissa should be there. We're starting at 2, so you guys have about 10 or so minutes to, do what you need to do. Take a little bit of a breather. All right, have a good one.